Hey everyone, it's Joanne. Hey, I'm making a video about our centroid and center of mass and gravity topic. So I'm on the module now, and the first thing I'm going to do is go to the overview. And in this module, you'll learn how to solve for the centroid and center of mass and gravity for composite bodies. We're emphasizing in statics composite bodies because often as engineers we're designing something that has multiple parts, or we have a piece of metal that's been machined and it has many different shapes inside it. And you've already figured out, or you learned in math and or physics, how to solve for centroids and center of mass and gravity, but we're concentrating on it for composite bodies. So let's start looking at this. And some of this might be a reminder, differences between centroid, center of mass, and center of gravity. Although the location of all of these are often the same, the centroid, the center of mass, and center of gravity are really based on different critical components. The centroid is based on a body's geometry. So if a body is a 2D body, then the centroid is based on its area, the area of the multiple bodies. If the body's a 3D, the centroid is based on its volume. For center of mass and center of gravity, it's not based on its geometry, but it's based on its material properties. Where center of mass is based on a material's mass, while the center of gravity is based on the material's weight. So I'm going to stop sharing for a moment and then share with you an Excel table that we're going to be working on today. So here we're typing in centroids 2D, centroids 3D, and then center of mass, and center of gravity. So centroid is based on geometry, and so is centroid, whether it's 2D or 3D. Center of mass is based on mass of the bodies, and the center of gravity is based on its weight. So in terms of, actually, let me write material properties here instead, and material properties here. So in terms of centroid for 2D, it's based on area. For 3D, it's based on volume. For center of mass, it's based on mass, and in center of gravity, it's based on weight. So it's important to know the distinction between these. Okay, so now I'm going to go back. I'm going to stop sharing, and I'm going to go back to the overview. Okay, so now we understand the differences between. Now the next thing we have to do is know how to calculate the centroid of area, centroid of volume, center of mass, and center of gravity. And these are my own abbreviations. CG is typically used for center of gravity, but centroid of area and centroid of CA, CV, and CM, I'm just using for simplistic sake here. So if the body is a 2D body, you're going to need to specify the X and the Y distance to the centroids and the centers. If the body's a 3D body, you're going to need to specify the X, Y, and Z to the distances, to the location rather. The distances are specified as X bar, which an X with a bar over it, Y bar or Z bar. And then in order, number 3, in order to calculate them, let me show you how. So the center of gravity of a composite body for X bar, it's going to be it would be the sum of the X bar times the weight for each individual body, and then it's divided by the sum of the weight of all the bodies. Y bar, the sum of the Y bar times the weight for each of the individual bodies summed up, and it's divided by the total weight, and then it's the same for Z. So if we're actually trying to calculate center of mass instead of center of gravity, then we would put M, we would use the mass here instead of the weight in the equation. For centroid of volume of a composite body, you see the equation is exactly the same, but instead of looking at weight, I'm looking at volume. And as you could assume, centroid of area is the same equation, but it's with area. So what we're doing for each one of these is we're summing up the centroid, center of mass, or center of gravity times the critical component for all the bodies or parts in the design, and then you divide it by the total of whatever the critical component happens to be. And it's most efficient to solve these problems using Excel or something similar. I think it's called Google Sheets, if many of you use Google Drive. So Google Sheets you can use as well. But I'm going to use Excel. So I'm going to stop sharing here. I'm going to go back to the module actually. And I'm looking now under our class notes, I'm looking at values. So I'm going to open this up. And actually, yeah, I'll open it up. I have to stop sharing it. I'm going to open it up as a PDF instead. Okay, we already know the centroid location for squares, for rectangles, and triangles. So here are some other centroids that you'll need to know. So an arc is a portion of a circle. So this is a portion of a circle, as this is an arc as well, but it's a quarter of a circle. This is solid filled in. So these are all two-dimensional. This is a semicircular arc, and here's a filled in semicircle. Rectangle we know, triangle we know, and then here's quadrant of an ellipse. We have a parabola. We have portion of a parabola, portion of a parabola, and then we have another triangular area. And then if we're looking at centroids for three-dimensional objects, we certainly would know where it is, the X, Y, and Z are for a rectangle. We also would need to know what it is for a cylinder, semicircle, a triangular, rectangle, tetrahedron. And then there's a hemisphere, a paraboloid, I believe, and then a cone, and then a half cone. And we're going to see some of these shapes in the example that we're going to do. And then also you'll see examples in the text, and then you'll see them also in homework problems. So I'm going to stop sharing this now. And I'm going to go back to share in the Excel table. Okay, so I'm going to scroll down now. We're going to look at a problem. And it's a problem from the text. It's problem number 104 in chapter 5, and it says, find the centroid of volume in the X, Y, and Z direction measured from the origin. So the first thing is we look at this picture, and we see that this is really one piece of material. This is not glued on here. It was a piece of material that's been machined to have this shape. And we're looking at a centroid of volume. So we know the critical component is volume. So the equation we're going to be using is the sum of X bar times the volume divided by the sum of the volumes. Now, we're measuring the X, Y, and Z bar from the origin. And when you look at this problem, it might be a little bit confusing to see where the origin is. But notice the X axis right here lies on the top of this. The Y axis lies here. And this Z, had the line been continued, you would have saw it at the edge. So I wrote, just for clarity, that the origin is on the top corner where the vertical wall intersects the horizontal plate. Okay, so the origin is right up here on top. So we look at this and we say, well, it's not really a composite body. It's not a bunch of parts. It's only one machine part. But in order to calculate the centroid of the location of this part, we really need to divide this up into sections. So if you think of it, and we could do it in many different ways. I'm going to try to do it in the shortest amount of sections, but I'm looking at a rectangular shape here with a hole. That would be another part, another section. There's also a rectangular shape here. That's going to be my third section. There's a semicircle here, and then I have a circle or a cylinder up on top. So that's how I'm going to look at it. So I'm going to scroll down on my table, and I set up the table already. So notice, my first column of my table represents the section. So section 1 is this vertical wall, okay, the vertical rectangular wall. The second section is the hole in the vertical wall. The third section is the rectangular horizontal plate. The fourth one is the semicircle horizontal plate. And then the section 5 will be this circular horizontal plate. So the first thing, so first column is the section. I certainly could have drawn it and just wrote where the sections are, but instead I put them in the description here. So in fact, let me just write description. It's probably easier if you just redraw it or just put the section 1, 2, 3, 4, and 5 on the diagram itself. And then you don't need this vertical column, the column. Okay, now let's look. The next column of my table is whatever the critical component is. This we're looking at a centroid of volume, so the critical component is volume. If it was two-dimensional and we're looking for centroid, the critical component would be area. If it was center of mass, it would be mass. If it was center of gravity, it would be weight. Okay, and here's my X bar, Y bar. Let's X bar, Y bar, and Z bar. So let's do those first, and then we can talk about the other columns at the end. So for section 1, what is the volume here? The volume is 100 times 120 times it's 10 wide. Okay, and notice at the top, I'm putting in the unit, so I don't have to write the units a bunch of times. Okay, what about the whole? The whole is going to be pi r squared, right? So 315 times, and the radius here is 30, so it's 30 squared. However, the whole in this case is actually a whole. It's really a subtraction of volume, so you have to make sure that you put a negative in front. So the volume for all the other pieces are going to be a positive, but the volume for this whole is going to be negative. Okay. Would you guys like, maybe you would like this to be in larger font so you could see it better. Yeah, that's better. Okay, rectangular horizontal plate. So that's 60 times 120 times, it's also 10 millimeters. And then the semicircular is 1/2 times pi r, and r for that semicircle is 60 squared. So 1/2 pi r squared. And then the last one, the cylinder plate up on top is going to be equal to pi r squared. So 3.14 times, and the radius is 40 squared. Okay, so now we have the volume of all 5 of those things, and we summed it up. So the sum here is a sum of all of them, taking into account that this is a negative. Okay, now let's look at the X bar. So X, you see where the X-axis is? Let me just go up a little bit. The X-axis is right here. So, and I'm measuring everything from the origin, okay? So for the vertical wall, going in the X direction, since it's 10 wide, X bar is going to be 5. And that's the same for the whole, it's 5. Okay, for the rectangular horizontal plate, it's 60 over, so it's going to be 30. For section 5, it's going to be 60. I'm going to put 60 in here. Okay, and then for the semicircle, well, now we have to look it up. So we know it's going to be 60 plus something, whatever the centroid happens to be. And maybe I should pull that up. So just hang on a second. Just hang on, I'm going into semicircular area. I'm copying it into my Excel table. I'll put it over here. Insert. Look. Okay, so in order to find the centroid, y sub c, right, because I'm going along the x-axis, it's 4r over 3 pi. So let's go back to this one. So it equals 60 plus, parentheses, 4 times pi divided by, oh, sorry, it's 4r. 4r and the radius is 60. 4r, and I'm going to put another parenthesis in here. Divided by 3 times 3.14. Let me just check. So it's 60 millimeters plus 4 times r, and the radius is 60. 4r divided by 3 times pi. Okay, so that's what x bar is. Okay, let's look at the y-axis now. Here's the y-axis, and I'm measuring from up here. So when I am measuring down for these two pieces, it's going to be 50, and it's negative 50, and negative 50. How about in the y-axis for this plate, it's going to be negative 5. Negative 5. And that's going to be negative 5 as well. So are you seeing that? The thickness of this plate here is 10, and the origin is on top of this plate. So the center of gravity, or the centroid, of both of these two pieces are going to be 5 millimeters down. How about this one? This guy is going to be 5 up. Okay, now let's do z bar. So z now is along this way. Oh, this is going to be easy. They're all 60 over. How nice. So we actually know, we know that the centroid of this composite body is going to be 60 for z bar. Okay. So now, remember what the equation was. Hang on. Let's go back, and let me go to my overview, and let me pull out the equation. Copy it into my Excel table. And here's the equation. Let's make it a little bit bigger. So we are looking at, the question was for centroid of volume. Here is my total volume, but I have to sum up, I have to multiply the x bars times the volume. So this column right here is the volume times the x bar, volume times x bar. This one is the volume times y bar, and this one is the volume times the z bar. So what is in here, the volume times x bar, is going to be my numerator. So I totaled them all up, and notice that the negative volume is still coming out here. So what I'm doing is I summed up the total x bar times the volume, y bar times the volume, z bar times the volume, and then I totaled the volume here. So what I want to do is take this total and divide it by the total volume. And that's what I did here. So for the part, this whole part here, X bar is the sum of the V bars times the X bar divided by the V bars and comes out to be 17.67 millimeters. The Y bar is negative 31 and the Z bar is 60. So let's take a look at, does that make sense to us? Well, we already mentioned that in the Z axis, the center of this whole thing is at 60, turns out to be 60. Well, let's look at X bar. It's probably going to be around here. And what does it turn out to be? 17. So it's going to be around here because look at all this volume that's all the way at the 0. And then Y bar is here. So it's definitely going to be lower, but it's going to be higher than the 50. So it's negative 31. All right. So to get more practice, there are 2 textbook problems, 2 example problems in the textbook. I'll change this too. So you could take a look. There's one of centroid of area and there's 2 centroid of volume if you want more practice. And then I just wanted to make sure that I got, yeah. And then what I created also is I created one of a table that has this blank in it. So you could use that. Okay, I'm going to stop sharing now. And I'm going to put this on pause for a minute. And actually, it might be the end of the video, but I'll come back on to tell you. I'm going to put it on pause. Okay, I found an error. I checked with my answers down below, and there's a problem. So I realized what it is notice here, I did put in a volume. Let's see, 3/4. No, I just put the area in. Craziness. So let's just take a look at this. So it's 100 times 120 times 10. This one, pi r squared, this is just area. I left out the width. I left out the 3rd dimension. Craziness. Okay, and this one I put in, and this one, I left out the 3rd dimension too. Okay, so now let me check my answers. 38, negative 18, and 60. 38, negative 18, and 60. Great. Okay. So now what I'm going to do is I'm going to clear this and just make sure that you put in the right units. I'm going to clear this, whatever the units happen to be. Actually, you know what I'll do? I'll put in units. Just make sure you're putting in the right units. And then this is going to be the critical component. In the case we did, it was volume, but it might be something else. Okay, so I'm going to save this now and I'm going to attach it to the module. Okay, I'm going to stop the video. Thank you. Bye.